Hello, this is Jagdish Marani, Product Marketing Manager for GemFire. Mike Stolz, who is the Product Manager for GemFire, and I will be going through many of the key features in GemFire. I'll start with a quick preamble and cover some of the industry forces and challenges that are driving the market need for in-memory data grids like GemFire. This will set the stage for Mike, who will cover GemFire's key features. When it comes to building great software, it is important that you're also really good at data, in being able to leverage big data and fast data in order to develop applications that change customer experience and develop new business models. Some of this requires a highly interactive, fast, and engaging real-time experience, which is exactly where an in-memory data grid like GemFire fits in. GemFire's performance features are a large part of what we will cover in this presentation. So, what are some of the forces in the market today that are driving the need for change and driving the need for GemFire? New applications that customers are building, especially if they want to become a data-driven company, get insights from the data and build in some real-time capabilities. So they're looking for continuous data flow and ingesting or streaming data. From a data perspective, we often talk about how to build some of these features like recommendation engines or a tip or an estimate of an arrival time of a package or something similar. This often requires the ability to get to that real-time data coming off a number of different connected devices, not just traditional systems. And we need to be able to pull that data in and make use of it in real time. We also need to be able to push that data back to the application and notify the application that something happened or something is available. It's a paradigm shift from a request-response pattern to an event-driven architecture. Self-learning smart systems refers to systems that learn from historical data, apply that knowledge to data that is being immediately transacted, and get real-time insights from live data. Data-driven smart applications have to be available 24/7. We can't schedule downtime anymore for these systems. Of course, we also need the ability to scale on demand and adjust capacity whenever it is needed. How do great companies harness data? When you look at companies that are really being successful in how they're working with data, there's a common set of trends that we can observe. First on the list is adoption of open source software. For decades, relational databases were used for everything. Today, with the explosion of various types of open source data management systems, successful companies are able to find the right data management system for the right type of problem that you're trying to solve. Increasingly, companies are adopting cloud-native platforms like Pivotal Cloud Foundry to make their software delivery lifecycle and operations faster and more agile. Cloud-native platforms are a large part of operationalizing 24/7 availability and being able to scale on demand. We also see successful companies adopting microservices architectures that allow teams to work autonomously by reducing dependencies on each other. This is enabled by the loose coupling between microservices and helps teams deliver much faster. Microservices are a key part of this DevOps and continuous delivery culture. This is a journey, and a lot of enterprises face challenges along the way. Some of the reasons enterprises are facing challenges on this journey are shown here. The first challenge is that application scalability is limited by traditional databases. This is especially true when it comes to high-performance, cloud-scale transactional data management. Then we have the notion of the disconnect between our analytic systems and our transactional systems, making the delivery of real-time insights very difficult. Another challenge has to do with being ready for cloud platforms that are driving massive scale and great reliability, but scale that our data layer isn't quite ready for. We'll dig into some of GemFire's key features and see how GemFire can help with these challenges. But first, let's take a brief look at Apache Geode, which is an Apache open source project that has its genesis in GemFire. Apache Geode is the open source version of the GemFire core. Pivotal started the journey to Apache's top-level project by contributing the core of GemFire to the Apache Foundation. The Geode project graduated recently in November of 2016 with the 1.0.0 release that came out, and GemFire, moving forward from this point on, has been and will be powered by Apache Geode. This is important for a number of reasons. There's been a significant shift in the enterprise software buyer preferences. First, enterprises have been through an era of vendor lock-in with proprietary software, And now customers are looking at open source software as a choice insurance policy that prevents vendor lock-in. Buyers are more frequently seeing open source software as superior to proprietary software, citing better quality, better security, more competitive features, and easier ability to customize and fix problems. The velocity of open source with faster and sustained pace of innovation is another reason. The R&D costs shared by the community cannot be matched by individual software vendors of proprietary software. These are just a few of the benefits of open source software. There are many more. GemFire, which is now based on Apache Geode, is a mature product with 10 plus years of R&D investment designed to deliver predictable low latency for high concurrent read and write access in a horizontally scalable and reliable way. It is used in mission-critical systems in many verticals, including trading systems and risk systems in finance, reservation systems in travel, web-based and mobile systems in banking, insurance, logistics, manufacturing, and many other verticals. GemFire is a key value in-memory data grid, which provides horizontal scale and achieves speed by being memory-oriented. It is cloud-ready and multi-site capable. GemFire is based on a horizontal scale-out architecture that scales by adding servers consisting of low-cost commodity components. We'll be going much deeper into GemFire in a moment, but before we do so, let's complete the picture by talking about a new in-memory managed service for Pivotal Cloud Foundry. The product that I'm referring to is Pivotal Cloud Cache, which is the first version of a caching as a managed service offering on Pivotal Cloud Foundry. Our goal is to make on-demand deployment as easy as possible. Hence, we are taking an opinionated, use case specific approach to delivering managed services based on our in-memory technology. Building each service for a specific use case allows us to preset defaults and minimize the configuration and customization burden. The first use case we're delivering is a look-aside cache. Cloud Cache will appear as a tile in the Pivotal Cloud Foundry marketplace. Our approach to Cloud Cache is different from GemFire. Cloud Cache and other related PCF services in the roadmap will be opinionated and use case specific. PCF administrators can manage the type of VMs available, and PCF developers can create their own Cloud Cache instances on demand. Let me now turn it over to Mike Stolz, who's going to go deeper into the GemFire key features.
So what is GemFire? GemFire is Pivotal's in-memory data grid. Horizontally scalable and elastic. You just fire up new nodes on the fly. Scale up or down, either direction, no downtime, no data loss when taking a node down. It's memory-oriented, but not memory only. It also supports a notion of disk persistence. It's active everywhere. No resources are left idle. All nodes are utilized by applications and users. You don't need a cold standby disaster recovery site. All nodes are up, serving data, and processing transactions. And it's a key value object store. It can store any kind of an object, Java, C++, C#, JSON documents, whatever. The enemy of performance is latency. Memory offers the lowest latency. Retrieving data from disk involves a disk seek and then reading from disk. You're talking about a total of 26 million nanoseconds. That's 104 times longer than the 1 megabyte memory access. And that's when the disk is directly attached to the node. In the case of network attached storage, reading from disk adds another 40x over the speed of memory. So the fastest way to store and fetch data is in memory. The claim that GemFire is 10x to 100x faster than traditional databases has been repeatedly validated in benchmarks. For example, the Securities Technology Analysis Center did a benchmark to prove that moving the compute into the IMDG runs 76 times faster. That's 76 times faster, not 76%, than moving the data to a compute grid as was traditionally done. GemFire can be easily configured to write to disk or a backend database, and this is usually done asynchronously to optimize performance. GemFire uses memory and peer members, other physical machines, in order to provide data durability and high availability and load balancing. This means that data updates can be guaranteed safe and recoverable in a matter of a few hundred microseconds, instead of the tens to hundreds of millis that it can take to make data updates to disk. Once this memory copy is made, each node can optionally write the update out to disk independently and asynchronously, guaranteeing a shared nothing architecture for your persistence layers. This technology has been used by the world's largest investment banks to create low-latency trading and risk management systems, giving their businesses the speed they need to improve the accuracy of their risk computations. In fact, JP Morgan won an award from the Banker magazine in London for innovation in data management technology when they began using GemFire in their equity derivatives event processing system to deal with timely cash payments and settlements. GemFire members discover each other dynamically when they are added to the cluster, and the cluster never needs to be shut down to add or remove capacity. This makes a GemFire node an ideal, lightweight, and flexible data management component in any cloud architecture. Clusters can grow and shrink dynamically. The cluster can automatically rebalance the data to reestablish the redundancy SLA after the removal of a node. At its core, GemFire has an event propagation engine that is ideally suited to event-driven architectures. The engine distributes data updates from member to member and out to interested clients. On both the client and the server, each event can invoke user code to process the update, called an event handler, and potentially spawn other data updates. Clients can hold their own caches, which can be kept up to date, and the stream of events can be easily used to build real-time user interfaces. There are a couple of different ways to handle events, including an approach that resembles pub/sub event processing on a standard message bus. These event streams can also be configured to be durable. This feature makes allowances for slow clients that cannot keep up to the rate of events and can tolerate the temporary disconnection of the client or interruption of the network while delivering every event requested. Event streams can optionally be conflated, removing intermediate events for the same topic so the client only sees the most recent state for each topic. Continuous queries give clients a versatile and rich SQL-like way of expressing which events they are interested in based on the content of the event. Instead of only being able to subscribe to topics, subscriptions can be based on the data payload itself. Note that the where clause is used only for expressing to the servers what events are of interest. The client is not polling for changes by running queries on a continuous basis. The event is detected from within the data servers in real time. Only the events matching the where clause sent by the client are sent across the network, preserving precious bandwidth and client CPU cycles. There is also an event sent the first time an update causes data that previously matched the where clause to no longer match, so the client can know that data has gone out of scope. These next two slides describe exactly how GemFire is able to provide sub-millisecond transaction capability, while at the same time providing the flexibility of horizontal scale. The key to doing this is co-location, providing a way that you can describe to GemFire which data is related and what the relationship is. In this simple example, we are going to partition or shard the data based on customer ID. So all data for customer A will be on machine 1, customer B will be on machine 2, etc. There will, of course, also be secondaries for each customer's data on another node, but for simplicity in this diagram, we will not attempt to show that here. Along with the customer data, there is other data related to the customer. Each customer has orders and shipments and payments. This picture attempts to show with the shading that we have co-located the related data with the customer record that is held on each machine. This co-location gives us the ability to perform even complex transactions like inserting a payment, updating a shipment record, updating the associated order, and maybe the customer record all at memory speed. This works for all many-to-one and one-to-many relationships. It's an unfortunate fact of life, though, that most systems need to handle many-to-many relationships, too. That's why GemFire has always had a notion of replicated regions. These are regions that exist to help satisfy many-to-many relationships. Some examples of such many-to-many relationships might be product descriptions. All customers need to be able to see all products. Pricing data, maybe inventory, for instance. This data is typically relatively small and doesn't update as frequently as the customer's orders and shipments. And that means that we can spray it across all of the members of the cluster, thereby making it available at memory speeds to any and all customers that the system is catering for. Data-aware function routing. GemFire provides for function execution co-located with the data. If you tell GemFire which customer you're executing the insert payment function for, it will execute the function only on the server that is primary for that customer. This allows data-intensive applications to have access to data at memory speed. The insert shipment function executes only on the machine where the particular customer's data lives, inserts the shipment, updates the order, updates the customer record, etc. The entire transaction will typically take under 1 millisecond to complete. Moving the behavior to the data instead of moving the data to the behavior is not only orders of magnitude faster, but significantly reduces the load on the network. GemFire also provides parallel function execution, which is a scatter, gather, or map reduce-like execution to provide massively parallel processing. Long-running functions and queries can stream results back to the client for truly interactive and real-time user interfaces. A request gets sent to all the nodes in the system for execution on the data that is local to them. And this is the way that all OQL queries in GemFire work as well. Let's talk about the consistency model. The consistency model within a GemFire cluster is always synchronous. A put operation will not be committed and successfully returned to the caller until both the primary and the backup have been successfully acknowledged as having been updated. Typically, GemFire is configured for write behind to any backing archival database by using the async event listener, which is asynchronous and fault tolerant using durable shared nothing persistent queues. This is an eventual consistency model for the archive. For those very infrequent cases where the database must be updated before the data becomes visible in memory, GemFire can be configured to update the backing database first before updating the in-memory image, guaranteeing that nothing gets seen in the memory image until it is safely stored in the backing database. Typically, remote clusters utilize the GemFire WAN gateway for situations where the distance between data centers is too large to do synchronous replication. The consistency model between two clusters located far apart is also an eventual consistency model. There is built-in collision detection in GemFire's WAN gateway implementation that can suppress storage of events that arrive out of sequence. Availability zones. The example in this slide shows a 9-node GemFire cluster spread across 3 availability zones. Availability zones could be just separate racks or could be very closely located data centers with a very good metro area network connecting them. Each availability zone in this example hosts 3 nodes of the GemFire cluster. In the event of the failure of any node or any whole availability zone, the cluster can continue to operate normally. And if you configure GemFire to hold 1 primary and 2 redundant copies of the data, you will still have 2 copies active and available, even if 1 whole availability zone fails. This can be thought of as recovery point objective equal to 0 and recovery time objective equal to 0. There is also a multi-geography capability in GemFire. This slide shows 3 clusters geographically separated and connected in a ring topology. This is a common arrangement for disaster recovery situations because financial services organizations and many other enterprises require separation of their primary and backup data centers to be at least 100 miles apart. That makes recovery point objective equal to 0 impossible without some intervening short hop forwarder, but the availability zones in the previous slide protect from all but an entire cluster outage across multiple AZs. Multi-site WAN gateway capability is frequently used to connect geographically separated distributed systems, 2 or more distributed systems that are loosely coupled. Asynchronous eventual consistency can perform at much higher throughputs than synchronous models. Synchronous consistency is way too expensive over the long haul. It can take hundreds of milliseconds to propagate 1 message from New York to Tokyo. That's an unacceptable amount of wait time for a transaction to complete. Based around the notion of a parallel, fault-tolerant, bidirectional store and forward gateway mechanism that takes events as they come, puts being the most important events, and it will take those events and queue them for reliable delivery. Queues can optionally be persistent. Each queue has a primary and a secondary server for fault tolerance. The built-in store and forward mechanism gathers batches of events and ships them across to another cluster. The receiving cluster acknowledges, and there's a handshake to confirm the transmission. You are presented with a facade that appears like it is all one system. However, each of the distributed systems actually behaves autonomously. Each site manages its own distributed system, and region data is distributed to remote sites using one or more connections. An important feature of WAN Gateway is that it is intended to be bidirectional. There's huge value to the bidirectional nature of the GemFire WAN Gateway. It makes fail back a whole lot easier. You don't have to do anything to fail back except to bring back your original primary site. It will transfer the latest information from the standby's queues, and then you can set the original primary to be active primary again. It's important to note that if you intend to be bidirectional and active-active, and your data access pattern has read, modify, write semantics, you need to implement a collision avoidance or detection scheme. One site might be primary for one business unit and the other site primary for a different business unit. Therefore, each has their own data set, and they are backing each other up for business continuity purposes. But there can never be a collision where both sites modify the same entry at the same time. Because the price of memory is getting lower and lower, it is becoming more and more common to want to handle large amounts of data in memory, so we've made enhancements that allow for a lot more storage in memory. The new Off-Heap feature of GemFire 9 enables you to store tens of terabytes of data in memory across a single cluster. If you try to store 250 gigabytes of data in a Java heap, there is a lot of processing overhead for garbage collection, and even occasional stop-the-world pauses. So what Off-Heap memory does is make the heap much smaller, typically smaller than 32 gigs. This takes away a lot of that GC processing overhead, so more memory can be utilized for storing and processing data for your application without the long GC pauses associated with the general purpose Java garbage collector. This memory is in the same process space as the JVM itself. It is just memory that the garbage collector doesn't know about and that is managed by GemFire's own proprietary free list manager. The 64-bit JVM with compressed OOPS enabled if you have your Java heap set to smaller than 32 gigs, performs better than the 64-bit JVM with larger than 32 gigs heap. The sweet spot for GemFire is to use the 64-bit JVM with less than 32 gigabytes of Java heap and utilize our off-heap in-memory storage to scale as large as you need. Integrated security in GemFire 9 is based on access points. GemFire client-server connections for access to data already was able to handle security for access to the data via server authentication and authorization. Now with GemFire 9, all administrative access made from GFish command line or via any third-party JMX-based or REST-based administrative tool are now able to be authenticated and role-based authorized. This was accomplished by adding authentication and authorization to the JMX beans and to the HTTP admin REST interface. All GFish, Pulse, REST, and JMX connections and operations can be authenticated and authorized with GemFire 9. Operations like viewing region data and performing data browser operations can be secured individually. Some users can read and write data, others can start and stop servers, and still others can perform backups, etc. Another new feature in GemFire 9 is the GemFire to Greenplum connector. The traditional approach to analytics has been to run nightly ETL jobs for data integration so that data scientists and analysts can use the data for analytics. This approach has some serious limitations, though. Businesses are increasingly interested in building applications that respond very quickly to business events. Nightly ETL jobs make it impossible to do any analysis on near real-time data. The best you can do is analyze and take action based on yesterday's data. Also, the results of the analysis are often never operationalized in a way that applications can take advantage of the analysis. Either the analysis is never operationalized or it is operationalized too late. Pivotal's new GemFire Greenplum connector provides a closed-loop environment that doesn't suffer from the same problems as an ETL approach. Your transactional applications that require high-throughput, low-latency access to data can use GemFire as their OLTP data access layer. While GemFire is processing transactions, it is also writing behind all the changes into Greenplum in near time. GemFire retains the latest data in memory, and the write behind to Greenplum has very little impact on the running cluster. In Greenplum, your data scientists and data analysts can use any number of toolsets or APIs to analyze the data. The results of the analysis can be pushed back to GemFire so that any application that is using data from GemFire has access to the results of the analysis. A simple use case for this kind of bidirectional data flow is a near real-time recommendation engine. As Greenplum works out the complex relationships between customers who bought one product and what other product they also bought, it can update that information in GemFire, and applications can use that information in near real time to produce recommendations during transaction processing, thereby potentially capturing upsell opportunities before they get away. Also, GemFire's event-driven architecture can raise events based on changes in the data so that applications can be on the receiving end of these events and are able to benefit from near real-time analysis. This hybrid configuration, enabled by the connector, utilizes each system for what it does best. GemFire is used for processing transactions at scale, and Greenplum is used for analytics and predictive modeling at scale. This wraps up the GemFire features presentation. Thanks for your time. If you have questions, please reach out to the GemFire product management team at gemfire-pm@pivotal.io.